to the ESRF, I think, from December 2000, and it's really has been a great boost for our research. The first thing I would like to, of course, thank some humans of the ESRF who have over the years been part of this research. Firstly, Andy Fitch from ID22, Manfred from ID13, Julie from 16B, Alexander Rath from ID19, and part of the ESRF, one cannot, of course, detach Paul Zaslansky from the Charité. Of course, I also want to thank my great research team, my students, my staff. Most of the work that you will see is done by my great students, and of course, they deserve all the praise for this. So we had really good background on biomineralization, so I will not take your time on that. I will dive directly into the two case studies I want to look at. And I will start with the brittle star. I will just mention again or stress what I have in my title. I really believe that in order to study biomineralization, we cannot just go to one beamline. I think that often what we have to do, we have to use complementary methods, different beamlines, and often also other methods such as electron microscopy. And I think it will be quite evident from this talk that you need to use these different methods together to actually get the main picture and understand the mechanisms in biomineralization. So I will start with the brittle star, the Ophiuchoma wenditi. And you can see here this organism, it has these 5 arms, and it has, on the arms, it has these single crystalline dorsal arm plates. And as you can see on this dorsal arm plate, you can see all these rounded shapes here. And each one of them, if you look in the cross section, it looks like this. It actually is a micro lens. And Joanna Eisenberg has shown that each one of these lenses can actually concentrate light onto a specific focal plane. And this actually serves as a multi-lens organ. And of course, there are many of these on each one of these arms. Now, calcite, we know is an optical material, but it has a drawback. And of course, it is a birefringence, as you can see here. This is along down the 104 direction. However, the organism actually grows each one of these lenses, or this entire single crystal, in such a way that this axis here is the 006 direction, or the C-axis of the calcite structure, which is the only optical axis that doesn't have this birefringence. So the first thing I would like to show you, this was done on ID 13, that if we take a cross section, a large cross section here of one of these big dorsal arm plates, we can actually now perform a rastering with a submicron beam, each one of these points. But if we take all the diffractions that we got from all of these points and we integrate them into one diffraction pattern, you can actually see that indeed it diffracts as a single crystal. So that's the first thing that we really need to know about these large crystals, or complex shaped crystals. The next thing I would like to show you is if we go to high resolution power diffraction, you can see here the 104 peak of the calcite. If it was pure calcite, the diffraction peak should be in this position. However, you see this large shift in the diffraction peak, and this is due to the fact that it is actually rich in magnesium. So it is high magnesium calcite. And as has been shown by Emil Zolotoyapko and co-workers, you can actually very nicely correlate the exact diffraction peak position to the concentration of the magnesium that substitutes calcium in the magnesium calcite. So this is something with which we all the time have to remember, that the peak position can also be very, very finely tuned by the concentration of magnesium. However, if we start performing on this structure powdered dorsal arm plane, so this is not a single crystal now, we actually powder it, and you start performing in situ heating, and then taking a diffraction every time after the heating, iso-chronous annealing it for about 30 minutes. We cool it down again. You can actually see that as we do this, these peaks starts to change in the shape and in the position. Eventually, if you heat enough, you're going to get something that the average is, of course, clean of magnesium, almost clean of magnesium, and you have a lot of a big tail here behind. But more importantly, you see that at around 400 or 500 degrees, you start getting another diffraction peak here, which is actually something that comes from nanometric size crystallites. And if you calculate what should be, by Rietveld refinement, you can calculate what should be the percentage of magnesium, we find that this should have about between 40, 50, or 60, depending, magnesium atomic percent. Now, if we go back to the room temperature diffraction, before we actually heated it, and you put it on a log scale, you can immediately see that each one of these diffraction peaks actually hovers over something which is nano. And if you actually look at the full width half maximum, you can find that it is coming from something that has a size of about 5 nanometers coherence length. So now we go back to TEM. This is done, of course, at home, not in the synchrotron. And in TEM mode and in hard-F STEM mode, you can actually see that in TEM mode, these particles can actually be imaged. This is, of course, a single crystal matrix, but you see that you have these bright spots here. And in hard-F STEM, which is Z contrast, they actually are darker, meaning it's something which has a lower Z number. And other methods that we use this together with Pupa-Gilbert, with using PIM, we could show that these particles are rich in magnesium. We could use high-resolution SEM with nanosimps and image this, and also filtered or energy filtered TM. And you can see that you have a mixture here of lower calcium, magnesium calcium, and higher magnesium calcite. Another very important thing that we can correlate is what we did on ID22. We can do in situ heating in the TEM. And you can see that these nanoparticles, which are rich in magnesium, are actually growing because of diffusion. They're actually sucking out the magnesium from the matrix. And at the end, you get large crystals, which are even faceted. So you start off with something which is about 5 nanometers, and you end with something which is even 40, 50 nanometers. But if you look at the pristine structure, so this is part of the lens. First of all, you can see that electron diffraction of this entire area indeed diffracts the single crystal, as we saw. But you can see now these the high resolution image, and you can see these nano particles that are, of course, rich in magnesium. That's why they are lighter in contrast, but they're completely coherent with the matrix. And if we perform an FFT on the lattice image at different areas, you can see that they're all exactly the same as the electron diffraction. So we have a single crystal, huge single crystal, and inside you have all these nanoprecipitate, which are richer in magnesium compared to the matrix, and they are completely coherent, which we saw on ID22 by having this nano hump beneath the diffraction peaks. And again, here you see this in high resolution TEM. So I'll just give a quick model. What we have here, we actually have a matrix that has low magnesium with nanoparticles coherent in the matrix with high magnesium. As I showed you, magnesium causes a contraction of the unit cell. And if the interfaces are coherent, then of course, you're going to exert compressive stresses on the matrix using a very simple model of spherical nanoparticles with a radius of R0. From Rietveld, we, of course, post-heating, but we can say that we have between, I would say, 6 to 8 volume% of these nanoprecipitates. And immediately you can find the correlation in this simple model between the average distance from center to center and this R0. And you find it already with 6 volume%, L over R0 is 4, meaning that if this is, let's say, 2.5 nanometers, the average distance between these particles will also be about 2.5 nanometers or 5 nanometers. So you can see that even 6 volume% is actually sounds like a small amount, but it's probably quite a high percentage to compress the entire matrix. Now, if you look at a proposed phase diagram for calcium, for calcite and magnesium calcite, you can see that actually in equilibrium, the solubility of magnesium is very low. There's some debate about it in literature, but we're talking about a few atomic percent only. Now, we're talking here about particles which are much richer, could be 40, 50, up to 60% even in magnesium, and a matrix is about an average about 15. The average, the matrix is about 13. So I think that Virginie already touched on this in her talk, but the only way to really get high magnesium calcium carbonate, as we see it, and of course everything is formed in room temperature, is going through an amorphous phase. And then when you crystallize it at ambient conditions, a lot of the magnesium gets actually trapped inside, and you get a supersaturated crystal. Now, this of course reminds us of something in classical metallurgy, and this is aging. If you take an aluminum copper alloy, of course, we know that in order to harden this material and strengthen it, you go to an area where you have a solid solution. This alpha here, you have copper, which is soluble within the aluminum. If you heat it up and then quench it, then you have a supersaturated alloy. And then by giving it a bit of diffusion, by heating to a lower temperature over time, you start getting these nanoprecipitates. You have the theta phase and the theta prime phase and so on. But at some point, they are coherent. And if you allow them to grow with thermal energy, grow too much, then you actually lose this coherency as they grow. Something very similar is happening to our system, of course, not by heating or by cooling, but by going through an amorphous phase, which is supersaturated, of course, in magnesium. It crystallizes, you have high magnesium in the lattice. We'll soon talk about how you get these nanoprecipitates. But once you have these nanoprecipitates, if you heat them, they grow, they stay coherent, but at some point when they grow, of course, because this elastic energy, you lose coherency. And if you make simple calculations, you can actually find that this loss of coherency should happen somewhere between 20 and 40 nanometers, which is exactly what we find also by powder X-ray diffraction and by TEM. So this is actually a way of really compressing, pre-compressing our brittle calcite, of course, on a nanometric scale, which is similar to what we can have on a macroscopic scale with tempered glass or with pre-stressed concrete. So here you can see the calculations of the compressive stresses. Now, we move this actually on a bit further, and we actually looked at the cross-section of one of these lenses that you can see here. This is again on ID13. And again, we can raster through different areas of this lens, have a diffraction pattern at each one of these points. And when we do that, we can do several things. The first thing we can do, we can actually map the lattice parameters across this cross-section. And I think you can immediately see, of course, we have some alignment issue here between left and right, but you can see that in this direction, you have layers, alternating layers of higher and lower D spaces, okay? So something is actually happening here within this single crystal, and it's not homogeneous. And again, if you look at the SAX signal, you can also see some of these layers. And I will not go into the details, but you can also understand something that we saw in the TM, but you can actually see it also with SAX, that these particles are most probably platelet-like and also oriented. So then we went to ID16B, and we imaged, we got the nano-tomography. And when we do that, we actually can see, here you see several of these lenses. You can see these alternating layers, but here we get contrast that comes from a change or modulation in density. And we believe, of course, that these layers are the same layers that we saw in the diffraction maps. And they obviously come from modulation in the magnesium concentration. Going back, I mean, we saw it for the first time actually from these holotomography images. We went back to the SEM, or this is the fib in the SEM, and we did very careful work with the backscattered electron imaging. And you can actually see that you can see some of these layers, or the contrast of these layers with backscattered electrons. However, if we start digging into the sample with the fib, you can actually, I hope you can see that these layers continue also within the volume. And here you can see some like growth line that we saw before, but of course we have alternation of magnesium concentration. And it's not only true for the lenses themselves, we actually take other skeleton parts like the teeth, we can take the spicules, and we can actually see this is present in all of these skeleton elements. And we can see the same thing also with TEM and with powder diffraction. So then we did XRF tomography, also on ID16B. Of course, we couldn't do magnesium because we don't have a vacuum chamber there, but we looked at the modulation of different elements, but also of calcium. And you can see the modulation of calcium. Of course, we believe that this, when calcium goes down, magnesium goes up, but you can see this modulation, and the periodicity fits beautifully to what we see in the contrast and the different methods, also in ID13, and of course also here in the density contrast from ID16B. And here you see another image where you can actually see these layers and each one of these lenses. So we tried to see these layers also in the TEM. In the TEM, it was extremely complicated to actually image this for various reasons. At the end, in the Titan, by really going to a low dose of electrons and a lower energy, we could actually see these layers, I think we could even see finer layers within the big layers that we see in the tomography. So that actually several hierarchies of these layers. But I think you can see here that these layers are not just composed of a higher concentration of magnesium, but you actually have alternating concentrations of these magnesium-rich nanoprecipitates. And that is actually what is changing the overall difference in concentration in magnesium. So it's actually the different concentration of these nanoprecipitates. Now, of course, this has a very strong effect on mechanical properties. We know that calcite is brittle, but we find that the cracks here, when they start propagating within a lens, this you can see also in tomography here, it actually goes through one of the layers and then it kind of rides on the interface between layers and so on and so forth. So it actually, many of these cracks don't actually go through the lens, they somehow hover between the layers and just go out and just kind of peel off layers from the lens. And this is, of course, due to the alternation of the compressive stresses between the different concentrations of these nanoparticles. So here I want to try and explain the mechanism, at least the way we understand it now, of how we even get the formation of these nanoprecipitates. And we actually thought about it quite a bit, but when we actually take the thermodynamical data, we could find actually published data on magnesium calcite. And of course, this was not done for amorphous magnesium ACC, but it was done for crystalline, but nevertheless, we think it shouldn't have a huge effect. If we look at the mixing Gibbs energy, and of course we look for the second derivative and look when it is negative, we can actually find that indeed there are two compositions that we can look for and find spinodal decomposition, meaning that anything between 14 and 48%, more or less, is unstable. And of course, if you give it the opportunity, it will decompose to lower and higher magnesium calcites. So this is what we think is happening in the amorphous phase, the precursor, which is like a gel. So you have diffusion there. In the beginning, you get this separation, then you get these droplets. These droplets are, of course, richer in magnesium. So you have a matrix of low ACC, magnesium ACC, and high magnesium ACC. It's known that magnesium stabilizes the ACC. Therefore, we can estimate that the crystallization takes place in the matrix in the lower magnesium ACC. And because it's a single crystal, we know it probably had only one nucleating point. And then this nucleating point, which starts in the matrix, starts to propagate. And there are two possible mechanisms which might be working in parallel. One, you have these, of course, these nanoparticles now, these nanoprecipitates, which are amorphous. Some of them get attracted to the crystal, which propagates. Some of them get pushed out. As you are pushing them out, of course, locally, you are changing the concentration of them in the solution. And then again, you have them being attracted and pushed out. And then that's how you get this alternating layers of different concentration of these nanoprecipitates. And as the crystallization front goes through, it actually just goes through the matrix as well as these trapped nanoprecipitates. A second route that can be working in parallel or instead of this other one is that as you start growing the crystal, we saw that magnesium is not really soluble in calcite. So you have some pushing out of the magnesium from the crystal. And then when the concentration gets high enough, you have secondary spinodal decomposition and so on and so forth. And this is how you get maybe the finer layers I showed you in the TEM. We did some synthetic experiments to strengthen this. So we crystallized magnesium calcite via an amorphous precursor with different concentration of magnesium in the solution. And I think we're just looking at the 104 peak of calcite here, but I think you can see that you have peaks, diffraction peaks in low magnesium calcite. You have diffraction peaks in high magnesium calcite, but you see that somewhere in the middle, you indeed have a gap. Nothing really forms. So this could actually be indirect evidence that indeed you have, in this case, you have spinodal decomposition. And here in the TEM, you can actually see something that might look like these nanoprecipitates, rich in magnesium in a synthetic assay. But we also did amino acid analysis of the proteins which are within these single crystals in the brittle star. And it turns out that they have at least one-fold, if not more than one-fold, less intracrystalline organics than other biomineralized tissue that we have looked at. And we were wondering what the reason is for that. However, if we take the same experiment and we add now some amino acid or polyaspartic into the solution, we find that we indeed can get stabilization also of magnesium calcite from amorphous phase somewhere here in the middle. So it could be that this whole play in spinodal decomposition also depends on the organics in solution. Another thing, this is actually unpublished data that we have done. We have also now performed Nano X-ray diffraction tomography on ID16B. And of course, here we have the 3D reconstruction. But if we take one slab and we perform X-ray diffraction tomography, you see that we get something that looks like a single crystal with very strange spots here. We'll talk about that. But we also have some rings here, which of course look like something polycrystalline. So first of all, we can index all of these rings and spots. But then the one thing that we can do, we can actually use a filter to filter out these rings. And of course, we can reconstruct the slab when we look at the entire integrated pattern. And you actually can see that we get now intensity from this entire area, including these spots that you see here on the surface, which is actually debris. Okay, this is particles of the lens that broke off when we prepared it and are just stuck on there, and indeed we can see them. However, if we filter out these rings and use just the single crystal pattern, and now we can reconstruct again, we see that we actually don't see these particles on the surface, and it means that these rings are not coming from the lens itself or from the dorsal arm plate, but they're actually coming from these particles which are stuck on the surface. So now we have the ability to filter these rings out, and we can now look at different spots after they are filtered and cleaned, and we can take now different diffraction spots, and of course we can reconstruct and look where they are coming from in this slab. As you can see here, these diffraction spots from the single crystal, they are elongated in the radial direction. And if you look here, you can actually see that it looks almost like it is split into two. So if you look here, you can see that there's a higher D space and a lower D space within each one of these diffraction spots. And of course, we can call them as strained, okay, and non-strained diffraction spots. If we just make a rough calculation, we can see that we have 3.5% strain along the A-axis and 2.9% strain along the C-axis, which is very high. I'll say something else. It is also very strange that we see much higher strain along the A lattice parameter, even though it has a much higher elastic constant than along the C direction. So this is very interesting. I might refer to it if I have time a bit later. But you can see here indeed that we have two types of peaks. One part of it is strained and the other part is unstrained. So now what we can do, we can actually reconstruct back, taking some of these doublets, the strained and the unstrained, and we can see where they're coming from in the slab. So now if we take the strain, you can see that it is more or less coming from the entire slab. Okay, it's more or less constant. However, if you take the unstrained part of the diffraction peak and you reconstruct it, you can see that it is very anisotropic. It's coming from very specific areas, okay, as you can see here. And then what we did is we actually went back to the holotomography, and we could look at these areas that had, so to say, unstrained lattices. And it was very interesting to see that those areas, for example, here, if you see, we could see a crack. Okay, so this crack, of course, we didn't notice it in the holotomography, but when we went back to the exact same position that we saw from the reconstruction from the unstrained peak, we could find that we have a crack there. And where the crack actually has propagated, we have relaxation of this strain. And of course, also on the surface, the areas that have relaxation of the strain are areas that have defects, and obviously it got mechanically damaged. So this is actually a very interesting thing that we have seen here that we haven't understood before, and we're still trying to fully understand it, is that actually when we powder these lenses, we actually relax part of the high compressive stresses that we see here in the hole, in the unbroken dorsal arm plate. And when a crack propagates, for example, it also seems to relax these high compressive stresses. So again, we have heated for 400 degrees an entire dorsal arm plate only for 30 minutes. We didn't relax all the strain, but immediately you can see that the contribution of this part of the diffraction peak, or spot in this case, that was strained is almost completely disappeared, and we only get, or almost only get, this undistorted diffraction spots. Now, we also found that when we take this whole dorsal arm plate and heat it, we start finding that as we relax these strains, of course, we also know the nanoprecipitates are growing, and we might be affecting the alternating layers. We find that we find popping out of many of these lenses that just disappear. So we also performed on ID19 in-situ heat radiography, and I hope this is going to work. So here you see the lenses on the right. In the beginning, they're intact. Of course, now, as we are heating, we allow these nanoprecipitates to grow. And I hope you will be able to see that, like popcorn, these lenses just pop out and almost like explode. Here you saw one that exploded. I'll make it go a bit faster, but I think you can see here that over time, many of these lenses have just popped off from the dorsal arm plate. So this is something we're still trying to fully understand, but I think it's quite interesting to see that you can actually see that the strain is very high within these single crystals. And also this X-ray diffraction tomography within a single crystal, not a polycrystalline structure, allows us to really see changes within the single crystal and different phenomena. Okay, so if I still have time, I will move on to the second case study. And this is helical microstructure of the mineralized coralline red algae. So we actually studied this structure mainly because it also has high magnesium calcite, and this whole idea now of having high magnesium calcite, understanding what happens in the structure is quite fascinating. The coralline red algae secretes high magnesium calcite, as I just said, and calcification occurs on the cell walls, and we have polysaccharides that serve as the framework for the crystallization. So here you see some examples. Now again, you can see by powder diffraction that indeed it is shifted compared to pure calcite due to the high magnesium. We have about 15 atomic percent, and also when we measure this from the position of the diffraction peaks, but also by EDS in the SEM and also by ICP. So here you can see a cross-section of this algae. You can see that it is highly porous. You can see the cell walls are actually made out of many nano platelets, as you can see here, so that different orders of hierarchy. And in TM, I will just show you that each one of these nanoplatelets indeed diffracts as a single crystal. And of course, I will talk about the mechanics in a moment, but already that the smallest building block here is made out of nanoplatelets. Of course, as Peter has shown in 2003, this is very important by the Griffith criteria to eliminate crack propagating via these crystals themselves. And this, of course, increases the fracture toughness. So now if we perform, again, nanotomography, ID16, you can see here cross-section, we can actually, from the tomography, we can calculate the porosity, and we find that it has at least 70% porosity. This is very important because it makes it actually a low-weight structure, which is made out of magnesium calcite. And the reason it has to have low weight is because it lives in shallow waters. It's, of course, connected to the ground, but then it all the time has to get, of course, sunlight, but it also is all the time under bending forces from the waves. And the calculated density, the upper limit is 0.8 gram per centimeter cube, which of course is lighter than water, and that is what allows it for the buoyancy to occur. But another very interesting thing that we noticed only when we looked at the nanotomography images is that these cells are not just open cells, but you can see that they are helical. This is an ID19, and if you look down one of these cells, you can actually see when we go down the 75 micron slab, I hope that you can see that they're actually turning around. You can actually see this helicity. And when we saw this with the tomography, we of course went back to the SEM. You can actually see here cross-section of the SEM where it is really helical. Another thing we did in order to really get a quantification of this, we performed ALD, atomic layer deposition. We deposited aluminum oxide inside these holes, these pores. We etched away the calcium carbonate, and we can actually see the helix or the negative of it made out of alumina, and we could get statistics on the helicity also by this method, about 67% pitch, 67 micron pitch. We did some finite element analysis. So we have the same porosity, once when we have cells which are just straight and one that are helical, and we can actually show, depending on the mode of loading, also a tangential and also compressive, we can find that we have up to 17% increase in the compliancy of a structure like this, just by having these helical open cells. And of course, this is very important for a brittle material, that to have the ability to be able to bend and not to break and not to crack. If I have just a few minutes, I will show this. We also performed high resolution power diffraction. Now, when we perform this heating, in situ heating in air, we just see the shift of the peaks. We don't see any formation of these nanoprecipitates that actually give a nano peak, diffraction peak here, which of course is rich in magnesium. And the reason is that magnesium calcite, especially when you have nanocrystals, is very sensitive to air. It decomposes to magnesium oxide, calcium oxide, and of course CO2. But what we can do on ID22, we can actually put them into a capillary, and we have 20 atmospheres of CO2, which actually eliminates the decomposition. And then you can actually see that also in this case, we get this peak here of a nanometric high magnesium, much higher magnesium calcite. I will not show it today, but we actually went back to the TEM, and we can find that within each one of these nano platelets, we indeed have high magnesium nanoprecipitates. And this takes us back to spinodal decomposition, which is probably a widespread phenomena in high magnesium calcite biomineralization. And we are seeing it now more and more in other mineralized tissue. Also this layering, as you can see here in backscattered electron, you can see these different layers. We can indeed show also here in TEM with EDS that we have modulation of the magnesium concentration. And of course, this of course can, as we saw in the brittle star, in this case, of course, it's not a single crystal, it's made out of, it's polycrystalline, but we still have a crystallization front, and we still have a very similar phenomena where we have this modulation of the magnesium, which eliminates crack, or to some extent eliminates crack propagation. So I hope I could convince you that you have here several orders of hierarchy. You have high magnesium calcite, which is harder than just calcite. You have these nanorods or nanoplatelets, and I didn't show you, but with each one of these, you also have nanoprecipitate with high magnesium calcite. You have this porous structure, which of course for lower weight, but you also still want to have it strong enough to withstand bending. I didn't mention it, but you also have varying wall thickness, where outside you have thicker walls, inside you have thinner walls, a bit similar to bone. And we also have this nice helical pores inside, which give it compliancy. So with this, I will end, and I will just say that we are, of course, anticipating the end of this pandemic, and of course, then we will welcome any one of you here in the Technion. Thank you very much.
Thank you, Boaz. Thanks a lot for this very nice presentation. I'm really glad to see the results of the diffraction and all the study that you perform on that. We have a few minutes for questions, so I think that Peter is raising his hand. So Peter,
if I may, thank you. So Boaz, I really like your precipitation study. There's one thing that puzzles me a little bit. I mean, in a system where you have both a variation in magnesium concentration and elastic strains, how do you distinguish between the two? So in other words, how can you be sure that it's a crack and not, say, a big inclusion with a different magnesium concentration, for example?
Yeah, so that's an excellent question, and of course we always have to make sure is the diffraction peak position due to magnesium or strain. So I didn't mention it, but we actually have in this system, at least, we have internal, I would say, internal standard. And we're quite lucky to do that. I mean, we have this debris that you can see here on the surface. And this actually comes from another lens that we broke. I didn't show it, but we can actually show that when you look at the lattice parameters that are coming from this debris that is already broken, we actually have the same lattice parameters as those of powdered samples.